Hello guys, welcome back to my channel Code Monger. So today we are going to discuss another interesting problem numbered 1584, minimum cost to connect all points. Okay, it's a problem related to the topic of graph, which is very interesting topic, right, in itself. Right, so let's try to understand the problem, what's being said, and how we can actually solve it. So you are given an array points representing integer coordinates of some points on a 2D plane where point of is equals to xi comma yi, right? So basically like we have been given an array, right, which contains coordinates, right, and these coordinate would represent coordinate on a 2D plane. Okay, and they have been given in the form like point of I represent the x and the y coordinate, right? The cost of connecting two points xi yi and xj yj is the Manhattan distance between them. Okay, so if we don't have to apply the distance formula, right, here we have to use the Manhattan distance. What is Manhattan distance? That is xi minus xj plus yi minus yj, right? uh, where mod represents the absolute value. Okay, so this would represent basically the distance. Return the minimum cost to make all points connected. This is a very interesting line, and which will give you a hint actually what we have to do in the problem. All points are connected if there is exactly one simple path between two points, right? So what I meant by this line is like the minimum cost to make all points connected. So let's say you see the example one, right? So here 4 points are given. Okay, 4 points are given, and now we have to connect all the points, right? We have to connect all the points such that the cost of connecting all these points is minimum, right? So basically from this line it's quite clear that they are asking about the minimum spanning tree, and that is also of such that the cost is minimum. Okay, so here normally what the cost represent is the weight of the edge. So normally when we study graph, right, so in let me take an example here. So what happens is like we have one node, two nodes, let's say, and then there is an edge between them. Okay, so this is v1 vertex 1, this is vertex 2, right, and this is e1, that is edge. So what's the weight of this edge, right? This is basically here in this problem is denoted by the cost, right? So this has to be minimum. Basically, that's what they have said. Okay. Uh, yeah, that's all. Okay. So one thing it's clear, like we have to find the minimum spanning tree. Now, do we know any algorithm which can be applied to find the minimum spanning tree, MST, right? How we can find the MST? So there are various algorithm, few of them like are Prems, right? Or you can say Kruskal, right? So all these algorithms are used to find the MST, minimum spanning tree. Uh, okay, so that's all there is to it, right? So let's dive into the problem to see how we are going to solve this problem. Okay, so in this problem, out of the MST algorithms, we are going to use a variation of Prim's algorithm. Okay, we will apply Prim's to this solution to find out the solution. Okay, let's go straight down to the problem. Now, what's being asked in the question? Okay, so in the question, now we know we have to find out the MST. To how we'll going to find that out, the what's the MST, right? In order to do that, there is a most important and the critical step, that is how we are going to denote our graph, right? So it is a graph related problem. Now we have multiple ways of defining how we denote the graph. It's like, according to me, like 30 to 40% of the problem decides how much the problem is going to be complex or easy. Okay, so you can define with the help of adjacency matrix. Okay, adjacency matrix or adjacency list, right? And in all of them, how you are going to define an edge, how you are basically going to denote the vertex, right, and the edge and all those things, right? And how you are going to store the distance, all those things, right? So how you come up with this is completely up to you. Over the period of time with the solving question, there are because each of the problem requires separate denotation, right? And if you try to denote your graph or represent your graph in some other way, then the effort in writing the code would be too much. But over the period of time, with experience, you would know what's the problem, and based on that, how you are going to denote it, denote or represent your graph, right? Okay, so in this problem, basically, how I'm going to represent it is basically I'm going to use an array, right? In that array, what we are going to have is three things. First of all is at which node right now I am at, 2 from this vertex to which vertex I am going, right? And the third is the distance or weight, whatever you can say, how much is the distance in this problem basically from at to 2 is. Okay, so this is how I'm going to represent the edge basically. Okay, so this is how my edge is going to look like. Now let's say we have this, these are the various in the first example, like these are all the 5 basically, 5 vertex are being given, and I have numbered them 0, 1, 2, 3 and 4. Okay, and the coordinates are also being mentioned. This is 0, 0, 2, 2, 3, 10, 5, 2, 7, 0. Okay, now the first thing, let's pick up any node. Okay, let's pick up any node. So let me mark this node as current node. Okay, and now we are going to process it. So the moment I have picked up any node, I will mark it as visited, right? This node is visited now because I am starting to process it. So from this node, what I'll do, I'll try to find edges from this node to every other possible unvisited vertex, right? So from this node or this vertex point of view, right now all the remaining vertex are unvisited. So I'll try to visit them one by one and mark their distance, and I'll also store their this edge value. Okay. Uh, okay. So let's say connected, I visited this node, vertex number 1. Okay. Now I visited that. Uh, Okay, I visited that, right? And the distance between, we have to calculate the Manhattan distance. So that would be x1 minus x2 plus y1 minus y2. So it would be 4. So 4 is the distance. Okay, fine. Now 4 is the distance. Now what I have to do is, like, I have to find edge between these two vertex, right? So between 0th and 3rd vertex. So find the Manhattan distance. So in this case, it would be 13. Fine. 3 minus 0, 10 minus 0, add both of them, 13. Now, Manhattan distance between these two nodes. So it will 5 minus 0, 5, 2 minus 0, 2, result is 7. Okay. Manhattan distance between these two nodes. So the Manhattan distance would come as 7 minus 0, and 0 minus 0, it is 7. Right. One thing I forgot to write basically is, like, we also have to mark it down, right? Note it down what the edge basically is. So this node was between so in this case the at was 0 and 2 was 3 node, right? So I'll write it down from, so I'll create a table here just for you to understand, right? What it is representing. So this is at, this is 2, right? At 2 and the distance between them. Okay, right now the at is we are we are at 0th node, right? So from here we are calculating distance to 3rd node, right? And the distance came to be 13. Fine. Then from 0 to 1, from 0th node to 1 node, the distance came to be 4. 0 node to 2 node, from 0 node to 2 node, the distance came to be 7. Then from 0 node to 4th node, right, from 0th node to 4th node, the distance came out to be 7 again. Okay, right. So this is how we have represented all our data. Now, the thing is, like, where we have to keep this data, right? Now, the next part of the problem is we have to find out the minimum pick out of all these edges, right? We have to pick the one which is of the minimum distance from this particular node, because that's how we are going to create a minimum spanning tree. So from this particular node, all the nodes that we have calculated, right, various edges that we have calculated, what is the minimum edge from this particular vertex, right? So to do that, in which data structure we are going to store this? Okay, so we are going to store all this data, okay, in a min heap. Okay, so we are going to store this data in min heap. Okay, all this data would be stored in min heap. So what's the benefit of min heap is, like, it will be able to give us the data in of log n time, right? Like what is the minimum value of all these things, what's the minimum value, and this min heap that we'll be creating, it will be on the basis of distance, right, of all the three zero and that at 2 and d, right? It would be doing the, or it will be popping out the element on the basis of the distance, because this should be minimum. Okay, so now what we have done is we have put all these data that we were calculating and putting them in the min heap. Now what we have to do, from this first iteration is complete, now we have to pick out the next vertex. So this one is processed now, right? This is ticked, this one is visited, this vertex is visited now. So from now we have to uh, take out the next vertex to process, right? In that case, min heap would help us. It will pick out the minimum distance edge from here and give us that. So we will strike this through, that we have picked it up from 0th node, we are going to the 1th node now. Okay, so this is the 1th node. I'll mark this as green, right, which would represent, like, this is one of our final path. Okay, so this is one of our final path. Fine. Now we are at node number 1. Okay, now we are at node number 1. The moment we reach here, we'll mark this as visited. So from here, now we have to find out edges from this to all other vertex which are unvisited. Okay, and as and when we do that, we have to keep pushing that edge into the min heap. Okay, so that we can have next edge for the further processing. Fine. Now we are at edge number vertex number 1, right? Now let's try to solve further. Okay, now we are at this. From this we will check out the 0th node, right? This is already visited, so we are not going to check this now. From first to second, right? First to second node. The first node itself, self edges are not required, so from the first node to second node we will check how much is the Manhattan distance. In this case it is 5 minus 2 is 3 and it is 0, so the distance is 3. Okay, so this distance is, Manhattan distance is 3. Now from first to third, how much is the Manhattan distance, that we have to find out. So 3 minus 2 is 1 and 8, so this is 9. Okay, and side by side we'll also put the distance. So from 1 to 2, 1 to 2 was 3, right? And then from 1 to third, the distance is 9. Okay, now from 1, right, from 1 to 4, right, the distance is 7 minus 2 is 5, 5 plus 2 is 7 again. Okay, so this distance is 7. So the node is from 1 to 4 and the distance is 7. Fine. Okay, now this node is also processed, or no other vertex that is unvisited is remaining. So now we will go to the min heap and pop the one with the minimum distance, right? So which is the minimum distance of all these three? Of all these, right? It's 3. Edge between 1 to 2 and the distance is 3. So let's mark it as green, right? So this edge is a part of the minimum spanning tree. Okay, now we are at vertex number 2. Okay, now we are at vertex number 2. Mark it as visited. Right, now we have marked it as visited. From here, all the we have to find out now the edges to all unvisited vertexes. Right, let's do that now. So from 2 to 3, right, from 2 to 3, what's the Manhattan distance? So 5 minus 3 is 2, and so that is 2 plus 10, 8, right? So the total would be 10, right? So distance came to be 10. So that would be vertex from 2 to third is 10. Now this vertex from 2 to 4, right? So from 2 to 4, right? The 2 to 4, what's the Manhattan distance? 5 minus 7 is 2. So 2 plus 2, it is 4, right? So this is 2, 2 into 4, right? Now, so from this vertex also, all other thing is calculated, which is unvisited, right? Fine. Now, what we have to do is like go to the min heap and pop out the next minimum edge, right? Next minimum edge. Now, from top we will go to 0 to 2, but 2 is already visited, so this one we won't take, right? So because 2 is already visited, so we are not going to again visit it, right? So that is fine. Then again there is a minimum is, sorry, right? So if we look at all the minimum thing here, right? So the minimum is from the edge that would be picked up is this fourth one, right? 2 to 4. Okay, so 2 to 4. This vertex of weight 4, right? This one was there. So we are going to pick up from 2 to 4, and this would be one of our final edges, right? So we are going to pick this, and this is going to be our one of the MST path, right? Okay, right. So this is the path. Now our current vertex has become as 4, right? So from 4, now what we are going to do, right? We are going to pop up all the first find all the possible edges from 4 to all the unvisited nodes and try to add it in the min heap, right? So let's do that. So there is one unvisited node remaining, so that is this one from 4 to 3, right? So the edge is from, so the edge is from 4 to 3, right? And the Manhattan distance is 4, and that is 14, right? 7 minus 3 is 4, 0 minus 10 is 10, and 10 plus 4, 14. Okay, so now we have to pick or pop from the min heap the minimum distance, right? Okay, the edge with the minimum distance. So let's do that. Let's see which is the minimum distance. So it is from 0 to 2, right? 0 to 2 and 7, with distance 7. So 0 to 2, but 2 is already visited, so we cannot take this one, right? Then from 0 to 4, right? 0 to 4 is having the minimum distance, but this is 4 is also visited, so we cannot take this one. Next is from 1 to 4. 1 to 4, right? So from 1 to 4, but 4 is also again visited, right? So we cannot take this one again. Then 7 is all processed. Then we have 1 to 3, right? Then 9 is the minimum across all of them. So let's pick up this one. Okay, so this is a valid one from 1 to 9. So this is the first node, this is the ninth node, right? Okay, so let's make it as a final MST path, right? So this is what it is. Okay, but now there are other edges are still remaining, right? Other edges are still remaining in the min heap. So what about them? Okay, so we need to know, right, from minimum spanning tree, right, how many, let's say there are two edges, sorry, two vertex v1 and v2 in our graph, right? So how many edges are there to represent MST, right? Only one edge is required. So for two vertex, one edge is required. Let's say there are three vertex, right? To create a minimum spanning tree, right? How many edges are required? Minimum, right? So that is for three vertex, we require two edges. Similarly, for four nodes, let's say these are four nodes. This is one, two, three, four. So minimum how many edges are required? So it is one to connect all the vertex, basically three. So for four we require three. So if we have to formulate how many edges required is equals to number of vertex minus 1. Okay, so here basically when we are processing or popping from the min heap, right? So how our iteration, how many iteration of all these things that we have to do, right? So that number of iterations would be equal to number of vertex minus 1, right? So how many in our case, right, what are this vertex represent? These vertex are basically the points. Okay, these are all the points are actually the vertex, or in you can say coordinates. So the coordinates are actually the vertex. So in this problem, if there are five vertex are given, so there would be four edges. So if you see the final result that we have represented in green, right? So one, two, three, four. So only four edges are required to create the MST, and after the fourth iteration, we should terminate our loop, right? So that would give us our answer. So I hope like the complete solution is clear to you, what I have explained it here, right? Now we are going to write the code for the same. Okay. So the whatsoever we have discussed right now on the right hand side, we are going to write the code for the same. So do follow along with me, right? If you have any doubts, query or question, do ask in the comment section. I'll be glad to answer. Okay. So let's start. Right. First of all, like find out how many vertex are there, right? So it is represented by points dot length, right? So we have all the points now. Now let's create a Boolean array to mark which are all the vertex are visited. Okay. Now we did that. Okay. So this is used to track all the um, vertex which are visited. Okay. Now let's create a min heap. In Java, we created with the help of priority queue. And as I mentioned, like how we are going to store the edges, that is very important, and I'm going to use an array for it. Okay, so let's create a min heap. Now we have new priority queue, right? And I'm going to write the comparator here itself. Okay, integer dot compare, it's a2 minus b2. What this is doing is basically is like to create a min heap. If I'm passing the array, right, and in my array I'm passing add 2 and d. So if you look at it here, what it means is like this would be a 0 index, 1 index and 2 index. So the second index, what is represented here, so it is at second index, right? So distance is used for doing the comparison, and that would be used by min heap to pop the next element. Okay, so whatsoever is the minimum, that would be pulled by the min heap. Okay, now what we have to do is like min heap dot add. So default value for the first iteration, right? We have to add something. So for that, it is going to be the zeroth, right? So this is just like a base condition, you could say, that we are entering in the heap so that it can start processing. Okay, then we are going to have int e is equals to 0. It will represent the edge and it will be used for termination also. And then we have answer is equals to 0, which will be used to calculate the final answer. Right, now we have to run the loop while h is less than equal to n minus 1, right? So this we discussed. Then we have to first thing that inside the loop that we have to do is we have to find out at which vertex we are right now, right? So in our case, I'll be starting with the what this base condition I meant was like from zeroth from zeroth vertex we are going to start the processing, right? So it is this. So in the array, right, we will be given multiple points. So from the first point we are going to start doing the processing. So we need to find out where we are right now. So for that we will do min heap that poll. So it will give us the first point from where we have to start the processing. Okay, and if we have already visited, right, the node where we are going to go, right? So from here, the first, as you see here on the right hand side, right? So what this one at of 1 represent is the point where we are, the vertex where we are going to go, right? So if that particular vertex is already being visited, then nothing is required to be done. We just need to skip it. Okay, because it's already being processed. We don't need to process it again. Now what next thing we have to do, if it is not processed, then whatsoever the distance that we have received, right, is at this node, at this edge, it would add it to our answer. Okay, so that's why we are going, because it will, if it is not already visited and min heap have popped it, min heap has popped it, right? So let's say the fourth, this edge was popped, right, from 0 to 2, the first instance this one was popped. So at that time we have to add this value to the answer because this green edge contributes to the answer. So that's why we are adding answer plus add to. Okay, now once that is done, our edge count would also increase, right? So what is happening is like now we have considered one edge, right? So we have to increment it and then we have to mark it visited also. The node that we have arrived at, right, we have to mark it as true, and because now it is visited. Now what we have to do for all the vertex present inside the graph, right, we have to iterate them one by one to see is there a potential edge from them to the possible answer. So that's why for all the vertex that we have here, right, 0 to n, we are checking from current vertex to all other from, let's say this one, from current vertex, right, to all other possible vertex whether there is a possible edge or not, and that edge is going to contribute to the answer, right? So I hope this part is clear. Now again here we are going to check, right, it could be possible like we have visited the node that we are going to, as you have seen in this case, right, when we were at the uh, when we were at this node. Okay, when we were at this node, in that case this node was already visited, this node was already visited, so we only need to go to this path and this path, right? So that's why the node or the vertex which are already being visited, so for them we don't have to do any calculation, we simply have to skip them. Okay, so yeah, now let's proceed. Now what we have to do, right, is we have to calculate the Manhattan distance. So that we are going to do it here. So int dx is equals to difference in the x is equals to math dot absolute value of points array, right? They have given us whatsoever is the point that we are, right? Right. So this is the basically, so 0 1 2 that we are getting, right, is the index of the points array, right? And we have to consider now x. So x would be represented at the 0th index minus points 2 of 0, right? So this is from 2, right? So from edge to the given edge, and we are subtracting the x, right? x1 minus x2 here we are doing. Okay, and then for y we will do the similar thing, is math.abs of points at 1 1 minus points 2 of 1. Okay, now we have to calculate the distance. It would be the sum of dx plus dy, Manhattan distance, and then we just have to add it to the heap. Okay, as a new edge that we have found out, and it would be from add to 1, right, 2 and distance. I hope this line is clear, right? So at 1 is right now where we at the current vertex to the next vertex that we are going to, and the distance, right? So this edge we will add and add to the min heap like we were doing here, right? So all these things that we are doing here, so the same is represented here, right, in the code. So that's it. Like if we simply return the answer, that was all to the problem. Let's try to see if I have not missed anything or done some silly mistake. Hopefully it should work fine, right? And okay, so it's points. Let's try to run it again. Mm. So it is okay, this bracket is misplaced. Now yeah, let's try to run it again. mm, Min heap again, this should be small h. Okay, fine. So all the basic test case are passing, right? So let's try to submit it now. Fine, great. So it is running with the 81 millisecond and it beats 75% of the solution. Okay, let's try to analyze the time complexity. Let's hope Leetcode would let us do that. Right. So the time complexity is O of n square log n. Right. So uh, this is what whole the solution was about. So I hope like the explanation was quite clear to you. If it is not, do ask me in the comment section. I will be glad to answer all of them, right? But this is like was a very great question in the interviews, so it would be good to practice this before going to an interview, right? So it will definitely help you. So yeah, that was all about this problem. If you have any questions, uh, do ask them, and do subscribe to my channel for more uh, interesting problems like this. See you in the next video.